Okay, we're just sort of backtracking, okay, for what we have had concerning mathematics of finance. And we have a holdover just from the first part, and this little item we have with annuities. And okay, for this held over problem, okay, we have for number 27, okay, we have for a child born this year, a 4-year college education at a public university is projected to be roughly $170,000. And assuming a 5% rate of return compounded monthly, about how much must be contributed to a college fund every month in order to have $170,000 in 18 years. Okay, and we'll be looking at the use of the traditional annuity formula where you're looking at where the future value is going to be the minimum, theoretically minimum amount, and just for what we have in the case of the setup. Okay, so we have for this item, okay, and it says here to round up to the next penny, not the nearest penny, but the next penny, if we don't exactly have an exact dollar and cents amount. And so for just setting things up, and I'll go ahead and put in the formula. Okay, so we got there we go. Okay, so for what we have here, okay, so in this arrangement, okay, we're looking at where the future value is determined. Okay, so we have so for A, okay, we're looking at $170,000. Okay, and we're solving for P. Okay, and now for the rate of interest, we can get N equal to 12. And the time span, okay, we're looking for 18 years. Okay, so for what we have in this item, okay, so we're looking at solving for P. Okay, and so we have with the numbers, say 170,000. Again, we have is equal to P times the quantity. And for 1 plus R over N, okay, so we're looking at 1 plus 0.05 all over 12. And we have to the n times t power. Okay, so n is at 12, t is at 18. And for what we have in the case multiplying by n over r, so we have n is at 12, r is at 0.05. Okay. And just looking at what we have after the substitution stage. Okay, so we got, again, we're looking at solving for P. And for what we have in terms of the sum within the parentheses, okay, so we have a decimal that's not going to terminate, okay, where we have 1.004. And then we have sixes that will repeat. Then we have to the 216th power minus 1. And for 12 over 0.05, okay, we can go ahead and simplify this to 240. Okay, all right, so for the activity, okay, so we still have 170,000. And for what we have, okay, inside the bracket, so for this small decimal number, okay, to the 216th power, okay, this number is going to be a little bit under 2.5. So 2.455 among the first digits. And again, we're going to subtract 1. . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . and we have times 240. Okay, so we have 170,000 is equal to P times, okay, and for what we have in the case of the difference within the brackets, okay, so I'm just going to display what I have. Okay, so that's going to be 1.4 55008 423. We have times 240. Okay, and again, we're still solving for P. Okay, so right now we're going to have 170,000 and for the figures on the right, okay, so we have so we had this number 1.455 times 240, and I'm just going to give the full display on this one. So we have 349.202 0215 times P. Okay, and to solve for P, I'm going to divide this decimal into $170,000. And for what we have, and putting in terms of dollars and cents. Okay, so right now we have on display case, we have, so you got 486 0.82421. Okay, and again, we're looking at rounding to the next penny. Okay, not the nearest penny. Nearest penny we have 82 cents, but again, we have to the next penny. Again, if you had the nearest, okay, we still have 82 cents, but just guarantee at least $170,000 at the end. We're looking at, on a monthly basis, okay, a contribution 486.83. Okay, so this is a case of what we have, okay, with annuities, okay, where you're looking at what your you already know what your future balance is going to be, or what the goal is going to be, and how you're going to get there, okay, through the monthly payments. Okay, and so in this case, we're looking at 486.83 to, have it safeguarded that, okay, would come out to a future balance of $170,000 in 18 years' time. Okay, now there was something with expressions, okay, and I had inadvertently left this one out, and we're looking at for expressing as sums and differences of logarithms, and we have from the study questions portion. Okay, so we have for this problem, we have in number 8. Okay, so we're looking at the base 5 logarithm. This particular ratio, which we have as a multivariable expression, and so just looking at what we have for this item. Okay, so looking at expanding and sums and differences of logarithms. Okay, so we have in the numerator, okay, we have 3 factors. In the denominator, we have 2. And, okay, so just looking at expanding. Okay, so I'm going to take care of what is at the top. So we got 7, so we can start out with the base 5 logarithm of 7. And anything that is attached in the numerator, okay, will be translated as the attachment of a distinct positive base 5 logarithmic term. So we have next plus the base 5 logarithm of t squared, okay, followed by the addition of the base 5 logarithm of u to the third. And with v to the fifth and z at the bottom, okay, we're going to have a couple of negative base 5 logarithmic terms. So minus the base 5 logarithm of v to the fifth. And we have minus, okay, the base 5 logarithm of z. Okay. And once again, we have converting from exponents to coefficients. Okay, first of all, I had the base 5 logarithm of 7. 7 is not an integer power or a multiple of 5, so in exact terms, this remains the same. For the next, okay, the 2 is going to be moved, as will the 3, and also the 5, for what we have in the variables t, u, and v. And so we have in the follow-through, okay, so we had the base 5 logarithm of 7. And we have followed by, okay, we have 2 times the base 5 logarithm of t. And we have plus 3 times the base 5 logarithm of u. Then we have minus 5 times the base 5 logarithm of v. And finally we have minus the base 5 logarithm of z. Okay, and now in continuing on, okay, with what we have been working with, okay, and we had with the part 2 set, and okay, so we looked at the first items, looking at the individual and logarithmic terms as well as the operations between them, and we had left off, okay, having completed the first 9 items. And for what we have in looking at logarithmic equations, okay, so we have for question number 10, okay, so we're looking at solving for x, okay, and we have for this item, okay, so you have a base 4 logarithm of the quantity of 3x minus 8 is equal to 1, okay, and here we have a single base 4 logarithmic term, and again, just setting the stage that we have here, okay, so again, we had the base 4 logarithm of the quantity of 3x minus 8 is equal to 1, and if we have a single logarithmic term, what we can do is that we can apply, again, our second property of logarithms, where upon we had a to the base a logarithm of x is equal to x. And here, if you notice in the setup, okay, we have the logarithmic base is going to be 4. And we have here, both sides of the equation can be treated as powers, to which the exponential base 4 will be raised. And just to mention, okay, I've said this before, and whatever you have in the result for x, we want to ensure that the attachment in the original equation will translate to something that is going to be a positive value. Okay, so taking care of the base 4 logarithmic appearance, okay, so treating both sides as powers to which 4 is going to be raised. Okay, so 4 to the base 4 logarithm of 3x minus 8. So we have 4 representing a, x represented by the binomial 3x minus 8. So the left-hand side is going to be at 3x minus 8. And to the right, we're going to have 4 to the first, okay, which is going to be 4. Okay, so 3x minus 8 is equal to 4. Upon adding 8 to both sides, we have that 3x is equal to 12. And with division by 3, okay, we're going to come out to x is equal to 4. And we can go back and check. Okay, so with x at 4, 3 times 4 is 12, 12 minus 8 is 4, 4 is greater than 0, so 4 does check out. Okay, now in the case of what we have with number 11, okay, and this one will have a little different twist to it, okay, and we got leading coefficients on both sides, and so for what we have in this one, okay, so I'm looking at -6 times the base 4 logarithm of the quantity of 5x is equal to -12. So we got the base 4 logarithmic appearance once again. And before I take the exponential base 4, I want to take care of the coefficient I have here with -6. So we have in this setup, what I can do is that I can divide the equation by -6. And upon doing so, we're going to have the base 4 logarithm of 5x is equal to 2. Okay, and again, before I get too far ahead, whatever I have for x, I want to ensure that 5x is positive. Okay, so now getting the base 4 logarithm of 5x by itself, I am now at the stage where I can treat both sides as powers, to which, once again, the exponential base 4 can be raised. Okay, so we have applying our second logarithmic property. Okay, so left-hand side, okay, had the basis 4, exponential and logarithmic will cancel, so we have 5x. To the right I have 4 squared, which will be 16, and for what we have for x, okay, we say we have 16/5 or 3.2 if you express as a decimal. And you can go back, so if you have like 5 times 16/5 or 5 times 3.2, we have 16. 16 is positive, so we have this number to be a solution for number 11. Okay. All right. Now, for what we have in the case of number 12, okay, and in this one, okay, so we have in this item, okay, so we got 4 plus the natural logarithm of the quantity of x minus 5 is equal to 3. And it says to round the result to the nearest hundredth. Okay, so we're looking at to the nearest 2 decimal places. And so for what we have in this arrangement, okay, so like what we had in the base 4 term, that is the logarithmic base 4 term at the start, okay, but for a different reason, we have this logarithmic term is not by itself, okay, for we got 4 added to it, and we can still nonetheless be able to isolate this logarithmic term. So we got 4 plus the natural logarithm, okay, we have of the quantity of x minus 5 is equal to 3, okay, and I can get the natural logarithmic term by itself. Okay, so if I take 4 away from both sides, so we have the natural logarithm of the quantity of x minus 5 is equal to, and we have 3 minus 4 is -1. And just with the logarithmic term now by itself, okay, and again I can take care of ln, or I can just rewrite ln in terms of the logarithmic base. Okay, so you have ln is going to be a logarithm base e. Okay, and so I can take care of the appearance of the logarithm, and upon treating both sides as powers to which the natural logarithmic base e will be raised. Okay. So for what I have on the left, okay, this will go to x minus 5. And for what we have in the case of e to the negative 1, okay, this number will have 0.36787. And if I isolate x upon adding 5, so you have 5.36787. Okay, but for what we have in terms of rounding, okay, so you have round to the nearest hundredth. Okay, so this will be to the nearest 2 decimal places. Okay, so we have 6 in the second decimal place, and next to it to the right is 7, and if the number alongside is 5 or greater, that signals that the number in that particular decimal place will round up. And so in this case, to the nearest 2 decimal places, we have x to be at 5.37. All right, now in continuing on with logarithmic equations, and we have for the case in number 13, okay, and this one, okay, so we have exclusively the presence of base 10 logarithmic terms. And in number 13, again, so they have the base 10 logarithm. Again, we have the base 10 logarithm of the quantity of x plus 5 minus that of the, what we have for 6 is equal to the base 10 logarithm of x. Okay, so we got base 10 logarithmic terms throughout. And here we have a single base 10 logarithmic term on the right, and we have 2 on the left, but I can make those 2 on the left into a single base 10 logarithmic term, again, whereupon subtraction will imply division. Okay, and I just want to mention, okay, for the attachments, whatever I have for x, I want to ensure that x plus 5 is positive, and also that x is positive. Okay, so in looking at consolidating, what we have on the left as a single base 10 logarithmic term, so we have with x plus 5 coming or being attached to a positive base 10 logarithmic term, we have this in the numerator in the combination, whereas for 6 this stems from a negative, so 6 will be on the bottom. And for what we have here, okay, so we have like logarithmic bases, and just as if you had like exponential bases, single terms, we could set the exponents equal to each other for exponential equations. Now, for logarithmic, we've got the same logarithmic bases, and we've got single terms on both sides, and this is going to signal that we can set the attachments equal to each other. Okay, so we can set x plus 5 over 6 equal to x. And looking at solving for x, and we've got x present on both sides of the equation. So what I can do here is actually just multiply both sides of the equation by 6, okay, so as to take care of the fraction. So we have 6's to go out on the left. So we have for this equation, okay, this will become x plus 5 is equal to 6x, and for what we have in the layout. So we combine our x terms. Okay, so I have 6x by itself, and if I join with x, so this will come down to 5 is equal to 5x. And with division by 5, okay, so this will be 1 is equal to x, or with x on the left hand side, we have x is equal to 1, and we can go back and check. And so for what we have in this case, right, so with x at 1, 1 plus 5 is 6, that is greater than 0. And x at 1, 1 is positive, so 1 is the solution. And it qualifies as such since it complies with all the requirements for the logarithmic terms to be defined. Okay, now in looking at now making the transition back to working with exponential equations. Okay, now for number 14, okay, this item can be worked in a couple of ways. So we're looking at the bases 32 and 64. Okay. And in this one case, so we have whereupon 64 is equal to 32 raised to the x minus 4 degree. Okay. And this could be treated in a couple of ways here. Okay. You can treat as an equation that has a common base. So if we look at this approach, I'll show you both ways here. So you got 64 is equal to 32 raised to the x minus 4. Okay, now, 64 and 32. Now, 64 is not an integer power of 32, but between 64 and 32, we do have a common base, and that's going to be 2. And if I were to rewrite 64 and 32 in terms of base 2, well, for 64, that would be 2 to the 6th. 32 is going to be 2 to the 5th. And 32 to the x minus 4, that would be 2 to the 5th, raised to the x minus 4. And applying the power property of exponents, so we have for 2 to the 5th raised to the x minus 4 degree, we have 2 to the 5 times the quantity of x minus 4. So you have 2 to the 6th, and for 2 to the 5 times all of x minus 4, okay, so you have 5x minus 20. And so for what we have now, we got single terms in the same exponential base, whereas the previous problem had the same logarithmic base. And we can set the attachments. In this particular case where we have exponents, we can write an equation with these sets equal to each other. Okay, so you have for 6 is equal to 5x minus 20. Okay, so getting the x term by itself. Okay, so if I add 20 to both ends, we have that 26 is equal to 5x. And we have with division by 5, we have that 26 fifths is equal to x. And so we have for this result, okay, we say we have x is equal to 26 fifths which you can also write as a decimal with 5.2. And okay, I'm just going to mention, okay, now there's another approach that can be undertaken. I'll just mention this. Okay, so when we looked at other types of exponential equations, okay, we had like methods used like if you didn't have a common base, but you could also use some of these approaches if you did have a common base. And if you notice for the variable x, okay, that is present only on the right hand side. And what you can do is that you can use the change of base formula pathway. Okay, so first of all, I can take care of the exponential base 32. So if I take the base 2, not base 2, but base 32 logarithm, and apply to both ends, okay, so for what we have now, taking this route, okay, so you're going to have the base 32 logarithm of 64 is equal to, and with the logarithmic and exponential bases going out, so we have x minus 4. And what I'll do here is I'll just switch the sides. Okay, so you have x minus 4 is equal to the base 32 logarithm of 64. And I can get this down to a numerical value. Okay, so for the base 32 logarithm of 64, I can use the change of base formula. So I can either apply natural or base 10 logarithms in the ratio. Okay, so we have, if I apply base 10 logarithms, so we have the base 10 log of 64 over, made that, the base 10 logarithm of 64 over the base 10 logarithm of 32. And this will end up as a terminating decimal. Which should be at 1.2. And guess what? With x minus 4 equal to 1.2, we still come out to x equal to 5.2. Okay. So this is another possible avenue in terms of solving for x in this type of problem. All right. Now, in the crossover, now we have with the remaining exponential equation in this set. Okay, so we're going back to the letter E, and it says to solve, okay, rounding to the nearest hundredth. Okay, and for what we have in this item, okay, so we're looking at solving for E, okay, whereupon we have E raised to the x minus 4 is equal to 4, okay, and in this one case, so we got the variable x on one side of the equation, and what we can do, okay, so we got E to the x minus 4 is equal to 4, so I can apply on both sides of the equation, okay, the logarithmic base, okay, that matches the exponential. Okay, so in this case we have a base e or natural logarithm. So for what we have on the left, okay, so you're going to have the bases e to go out. Okay, so this will become x minus 4. And we have is equal to the base c logarithm of 4. And again, a base c logarithm of 4 is going to be a natural logarithm. since we already had the natural log encoded, okay, we don't have to use any change of base formula. Okay, so we have in this setting case, you have x minus 4 is equal to the natural logarithm of 4. And among the first digits, okay, so you have 1.38629. And looking at isolating x, so we have for x, we have 5.38629. Okay, but in terms of the final answer, okay, so again, we're looking at rounding to the nearest hundredth. Okay, so we're looking at the dynamics that will play out, okay, around that number that's in the hundredths place. Okay, so we got 8 in the hundredths place. Next to it is 6. And if the number to the right is 5 or greater, which it is, okay, then the number in the position that is concerned, okay, that is going to round up. So we have for the final answer in this one, okay, we come out to 5.39. Okay. All right. Now for what we have in the case of the remaining items, okay, and this is going to be concerning systems of equations. I'll give you just some items here, okay, some which will be linear equations, others that will be nonlinear. And in case of systems of linear equations, okay, so we're going to have here, okay, for a system of linear equations, okay, and we'll be looking at just the variables x and y. Okay, say we have for a system, say we have a sub 1x plus b sub 1y is equal to c sub 1 along with a sub 2x plus b sub 2y is equal to c sub 2. Okay, and so we have for the system above, okay, so for the system above, okay, if there is one solution, okay, then you're going to have the graphs will intersect at the point xy. And we're talking about the graphs of these two equations. And xy will be the solution point. Now let's say that for systems of linear equations, okay, and I'll show you just kind of like two of the same kind of approach and one that's going to be distinct. Now let's say if you're looking at solving for x and y. And we'll say that for the first system. Okay, we'll say we have 3x minus y is equal to 3. And we'll say that we have for the second equation in the system, we'll say we have x plus y is equal to 5. Okay, and we'll use this notation to indicate both equations are in the same system. And if you notice, okay, with what's referred to as the addition method, okay, the addition method means that the equations can be aligned such that we can apply addition where we can cancel out one variable and solve for the other. Okay, so in this one, we can utilize what's referred to as the addition method. Okay, so if I add the equations, so we have 3x minus y is equal to 3. And we have x plus y is equal to 5. And if you notice, okay, we have negative and positive y will cancel each other if we add the equations together. So we have left over, we have 3x plus 4x. 3x plus x is 4x. And we got 3 plus 5 is 8. And now we have with 4x equal to 8. And we have upon division by 4. So if 4 times x is equal to 8, we're going to have the x is equal to 2. Okay, now that we got the value of x to be at 2, I can plug in 2 for x in either of these equations. And I think it might be quicker to go with x plus y is equal to 5, but you could do it likewise for the other equation. So you have x at 2. And if 2 plus y is equal to 5, if 2 plus y is 5, we're going to have that y is equal to 3. And we can check the results here. So you got x at 2, y at 3. So you got 3 times 2 is 6. And y at 3, so we have 6 minus 3 is equal to 3. And also we got x at 2, y at 3, and 2 plus 3 is equal to 5. So those values that we have for x and y, okay, that will be the combination that we seek, okay, for both equations to work out in the system. Okay, so we have for the solution, we can say we have x is equal to 2, and y is equal to 3, and I know like in Alex, it likes to put this in terms of ordered pairs. So we have for x and y, okay, so the graphs of these equations will intersect at that solution point where we have at the point 2, 3. Okay. Now, another type of situation where we can still apply the addition method, but we had to kind of use a little bit more elbow grease, so to speak, in terms of solving. Okay, let's say if we have x plus 3y is equal to 5, and we have that 3x minus 2y is equal to negative 18. Okay, notice before we had additive inverses in the first equation as well as the second, okay, when we had negative and positive y, but here we cannot add x and 3x or 3y and negative 2y and have either variable to cancel out. So what you're going to do is that you're going to eliminate So I'm going to eliminate one variable and solve for the other. By first taking multiples of one or both equations. One equation or both equations. Okay, so if we go back to what we have in the system, okay, so you have x plus 3y is equal to 5. And we have 3x minus 2y is equal to negative 18. Now, you have your choice, and you can work with either eliminating y to solve for x, or you can also eliminate the x terms and solve for y. Okay, but right now, let's say for x now, x and 3x, okay, if I were to add together, you would have 4x. But let's say if I wanted to eliminate the x and create the pathway to solving for y first of all. Okay, what I can do here is that between x and 3x, now, say to eliminate the x terms, okay, now x will not eliminate 3x, but what will eliminate 3x will be negative 3x. So I can make this x into a negative 3x if I take a multiple, in this case, a multiple that will be necessary to create a set of additive inverses. Okay, will be to multiply x plus 3y equals 5 by negative 3 while keeping the second equation the same. So if I multiply by negative 3, so we're going to have in the system's adjustment, so we have negative 3x, negative 3 over 3y becomes negative 9y. Negative 3 times 5, so that will be negative 15. And we still have 3x minus 2y is equal to negative 18. Okay, and here I can add the equations together. Okay, so if I add together, so you're going to have negative and positive. 3x will go out. And we have negative 9y plus negative 2y, so this will be a negative 11y. So we have negative 11y is equal to negative 15 plus negative 18, so we have a negative 33. Okay, so got negative coefficients on both sides, and we have with division by negative 11. Okay, so we're going to end up with y is equal to 3. Okay, so we have the solution for y at 3. And I can go back and solve for x. I can plug in 3 for y in either equation from the original set. And I tell you what, okay, now we adjusted x plus 3y is equal to 5, but I can go back to where I started from. Okay, so if I go with x plus 3y is equal to 5. Okay, now you can go with the other equation, but I think x plus 3y equals 5 will be a much quicker route to solving for x after already attaining y. So I'm going to plug in 3 for y now that y has been determined. So we have x plus 3 times 3 is equal to 5. Okay, so here we have x plus 9 is equal to 5. And if I take 9 away from both sides, we have that x is equal to negative 4. And we can go back and check. Okay, so x at negative 4 and y at 3. Okay, so you got x at negative 4, y at 3. 3 times 3 is 9. Negative 4 plus 9 is equal to 5. And we have with the other equation, okay, so x is at negative 4. 3 times negative 4 is negative 12. Negative 2 times 3 is negative 6. Negative 12 minus 6 is equal to negative 18. Okay, so we have for that solution, okay, so we have x is equal to negative 4 and y is equal to 3. And again, that as an order pair is just going to be one solution point. Okay, so these particular equations, okay, can pretty much be solved by using the method of addition. And there could be those where you could still use that, okay, but where you might go with another approach. And let's say that if we have as a third case, now solving for x and y, and we'll say that we have, in this setting, we'll say we have y is equal to 4x plus 3. We have also that x plus y is equal to 13. Okay, and if you notice, we have in the alignment, okay, we don't have x and y on both sides of the equation, especially in the first part of the system. And okay, and instead of having to rearrange the variables, okay, now the first equation we have with y isolated, and that is defined, okay, where we have like in the slope-intercept form, so you have y is equal to 4x plus 3. And we're still looking at the same values of x and y such that y equals 4x plus 3, and also where x plus y is equal to 13. So looking for the values of x and y such that we have these two equations to coexist. Okay, instead of the addition method, we can go with what's referred to as the substitution method. Okay, and so for okay, so you have y is already isolated. And what I can do here is that for 4x plus 3, which defines the first y, I can take 4x plus 3 and plug in for y. So in this particular case, I'm going to be substituting so substitute 4x plus 3 for y. And set up the second equation where I can solve for x. And if I go that route, okay, so we got x plus, okay, and for y, again, the parentheses are optional, I'm just stressing, okay, that we have 4x plus 3 in lieu of the y in the second equation. Okay, so if I add together, so you got x plus 4x becomes 5x. Then we have 5x plus 3 is equal to 13. Okay, and for what we have in the case of the follow through, okay, so if I take 3 away from both sides, so we have 5x is equal to 10, and with division by 5, we're going to have the x is equal to 2. Okay. Now that we have the value of 2 attained for x, I can plug in 2 for x in either equation. And since I had the first equation already in terms of y, I'll go with the first equation to solve for y. Okay, so if I plug in this time the known value of 2 for x, so here we're going to have y is equal to 4 times 2 plus 3. 4 times 2 is 8. And we have 8 plus 3 comes out to 11. Okay, so we have, with the apparent solution, we have x at 2 and y at 11. And just going back and checking. Okay, so if y is 11 and x is 2, 11 is equal to 4 times 2 is 8 plus 3. 11 is equal to 11. And also with x at 2 and y at 11, 2 plus 11 is 13, is equal to 13. Okay. So for the solution, okay, so we have x is equal to 2. And y is equal to 11. And again, just as an order pair, okay, so you have the solution point at 211. Okay, now in the case of what we have for, let's say if we go and cross over to the realm of systems of nonlinear equations. And we're going to have here, let's say that if we have looking at solving for x and y. And I'll just take one equation here, and let's say that if we have looking for the values of x and y, okay, such that we have x squared plus y squared, okay, we'll say is equal, let's say we have x squared plus y squared is going to be equal to 74. Now I have that x squared minus y squared is equal to 24. Okay, and if you notice, we can apply the addition method for you're going to have additive inverses with positive and negative y squared okay, so you have x squared plus y squared is equal to 74, and simultaneously, okay, we have x squared minus y squared is equal to 24, and so we can add both equations together. So we have here x squared plus x squared will be 2x squared. And we have 74 plus 24. Okay, this will come out to 98. And we have with division by 2. We're going to have the x squared is equal to 49. And guess what? So we got 2x squared equal to 98. And with division by 2, I have x squared is equal to 49. And if I go with the square root property of equality, so we have that x is equal to plus or minus the square root of 49. And 49 is a perfect square value. So we're going to have the x is equal to plus or minus 7. Okay, now, and we can solve for y, okay, and we can use either the two equations, and so what? Since I'm looking at having to arrive at y squared before I can get to y, I'll go with the one that has positive y squared. Okay, and so instead of having to back substitute for x and having to go through all the squaring, I've already got x squared stored with 49. So we have 49 plus y squared is equal to 74. And if I take 49 away from both sides, so yeah, y squared is equal to 25. And we have with the square root property of equality once again. So we got y squared is equal to 25. And in solving for y, say y is going to be plus or minus the square root of 25. And so we have that y is equal to plus or minus 5. So we're going to have for the solution, we're not going to have just 1 point, but what's going to be 4 points. Okay, and just in terms of what we have in combination terms, we have x equal to plus or minus 7, as well as y is equal to plus or minus 5. And if I were to draw out as separate ordered pairs, we have one combination where we have both x and y are positive. Also a couple of combinations where one is positive and the other is negative. So you have like 7, negative 5. As well as negative 7 and 5. And also we have with the remaining point will be where both x and y are negative. And so if you draw upon any one of these 4 points and take their squares, we have with all of these combinations, you had the sum of the squares at 74, and also the difference of squares to end up at 24. Okay, and just one more thing we have about equation systems. Now there was something we had a while back when we had like a consistent equation, inconsistent equation, and also what we have had with a consistent and dependent system, or what was in equation terms an identity. Okay, now and for what we have in the case of classifying systems of equations. Okay, so the first type, okay, we have a consistent and independent system. Okay, so for consistent and independent, okay, there is going to be a finite number of solutions. That could be just one solution, or it might be a couple of solutions. You can say we have for second category, okay, we have inconsistent. And an inconsistent equation system is going to be one that results in no solution. And then we have in the third, okay, where you can have essentially an identity. Or somewhere along those lines. We have with consistent and dependent. Okay, we're going to have an infinite number of solutions. Okay, so you have an infinite number of solutions. Okay, and let me just kind of give you a little breakdown of the categories. Okay, so we have if I were to determine the type of system, whether it's consistent and independent, inconsistent, or consistent and dependent. Okay, and let's say we have, first of all, we'll say that we've got, let's say we have x plus y. So x plus y is equal to 7, and negative x minus y is equal to 10. Okay, and so for what we have in this case, all right, so we got x plus y is equal to 7, negative x minus y is equal to 10, and if you notice, we have additive inverses for both x and y. And if I add the equations together, okay, so I have x and negative x will go out, y and negative y will go out. So left-hand side is going to be 0, 7 plus 10 is 17, and of course, that's a false statement. So for x and y, okay, there will be no solution. And the type of system is going to be inconsistent. And let's say that for the next equation system, okay, and I will say that I have here that I'm going to have in the layout. Okay, so I have that. Let's say that we have x plus y. Again, we'll say we have is equal to 7. And we have x minus y. Okay, that is going to be equal to 1. Okay, so for what I have in this layout, sorry, got to be able to see. We have x plus y is equal to 7, x minus y is equal to 1. And if I add the equations together, okay, so we have this time negative and positive y will go out. And I have that 2x is equal to 8. And from this, we have that x is equal to 4. And again, so we have for x plus y equal to 7, or as well as x minus y equal to 1. So we have 4 plus y is equal to 7. And from this, we have that y is equal to 3. Okay, so we have, in this case, for the solution, okay, so there's only 1. Okay, so you have x equal to 4, y equal to 3, and so we have, for the combination as a point, we have xy is equal to 4, 3. Okay, so there is one solution. Okay, and this type of system is going to be consistent and independent. Okay. Now, so we have with third scenario. Okay, so if I have the x plus 2y is equal to 7. And I have negative 2x minus 4y is equal to negative 14. Okay. Now for what we're going to have here, okay. Now I do not have additive inverses yet. But I can create or rewrite either equation or both equations where we are going to have additive inverses. Okay, so if I look at canceling out, let's say negative 2x. Okay, so I can raise the x to 2x, so I can just multiply the first equation by 2. So you're going to have 2x plus 4y okay, is equal to 14. Again, keeping the second equation fixed, okay, so you have negative 2x minus 4y is equal to negative 14. And guess what? Once we add together, we have complete cancellation, and this will come down to 0 is equal to 0. So that is going to be true. So that means you're going to have an infinite number of solutions for x and y. Okay, so we have, in the case of the solution, now I'm bringing this up, okay, because ALEKS kind of goes by its own set of rules. Now for x, we can say we have all real numbers. But now how it wants to express the solution for y, and wants y to be expressed in terms of x. Okay, so you have x, you have the set of all real numbers. But in the case of solving for y, so if I go back, if I isolate the y term, so if I take 2x away from both sides, so we had that 4y is equal to negative 2x plus 14. And if I divide by 4, in this particular case, right, so we have not 2x plus 4y. Going back to I was misreading that one. So you have x plus 2y, okay, is equal to 7. Okay, so I can isolate the y term. So you have 2y is equal to negative x plus 7. And we have with division by 2. So you can say that y is equal to negative 1/2 of x plus 7/2. Okay, so we have for the solution, you have x is going to consist of all real numbers, and while x we have for all real numbers, we'll have in line with x, we're going to have for y, we have negative 1/2 of x plus 7/2, and this type of system is going to be consistent and dependent. Right, so you solve for x, and if x has an infinite number of solutions, you're going to write either equation in terms of y. In this case, you have y is equal to negative 1/2 of x plus 7/2. Okay, now for rounding out, okay, what we have in the mix. Okay, so we have with systems of equations. Okay, so we have like in case of numbers 14 and 15. From the study guide portion, okay, in the first set. So we have for 14, okay, so you have 2x minus 3y is equal to 7. Okay, and we have also 4x plus 2y is equal to 26. Okay, and what I'm going to go ahead and do, okay, is that for, if you notice, okay, we have 4x is going to be a multiple of 2x, and I can create the pathway by using the method of addition if I adjust the 2x and make that into a negative 4x. So if I go with this route, okay, so I got negative 2 over 2x, so this would be negative 4x. Negative 2 over negative 3y, so that'll be plus 6y. Negative 2 over 7, so there'll be a negative 14. So adding the equations together, okay, so you have negative and positive 4x will go out. Now for what we have in the case of y, okay, so we have 6y plus 2y is 8y. Then we have negative 14 plus 26 is 12. Then we have with division by 8. We say we have for y is at 3/2, and that can also be expressed as a decimal. Okay. And looking at what we have in terms of solving for x. Okay, so if I go, let's say with the first equation, okay, so if I plug in 3/2 for y, and here we have 2x minus 9/2 is equal to 7. Okay, now 7 is going to be 14/2. So we have upon isolating 2x, okay, so we got 7 is 14/2. 14/2 plus 9/2 is going to be 23/2. And we have with division by 2, okay, so x is going to be 23/2 divided by 2, so this will be 23/4. Or 5.75. Okay, so we have for number 14, okay, there's going to be one solution. Okay. Again, I know that Alex likes the ordered pair notation. Okay, so you have for x and y. Okay, decimals also allowed. Okay, now for the other system, okay, so we have in number 15, so we got x squared plus y squared is 25, x squared minus y squared is equal to 7. Okay. There we go. Okay. Okay, now for this system, okay, we already have additive inverses in line with, once again, positive and negative y squared. So we just go ahead and combine the x squared terms. So we have 2x squared is equal to 25 plus 7, which will be 32. And we have with division by 2. Okay, so you got 2x squared over 2 becomes x squared. And we have x squared is equal to 16. And again, you can either solve for x by setting this up as a quadratic equation standard form and factoring, or again, you can utilize the square root property of equality. And if I okay, so x will be plus or minus the square root of 16, so I have for x, additive inverse solutions, okay, with positive and negative 4, and I can go back and solve for y, okay, and I can use either the first or second equation to isolate y squared, and then follow what I have in y. Okay, so I already have lined up that x squared is 16. I can just plug in 16 altogether for x squared in either equation. Okay, so I have 16 plus y squared is equal to 25. And taking 16 away from both sides, I have that y squared is equal to 9. And again, with the reapplication of the square root property of equality, so y is going to be plus or minus the square root of 9. And we have y is equal to plus or minus 3. So you have for the solutions. Okay, so you have x, you have plus or minus 4, you have y, you have plus and minus 3. And again, as order pairs, you say you have 4, 3. For negative 3, negative 4, 3, and also the last possible combination, so we have negative 4 and negative 3. And we have in terms of completing out. Okay, so you have with our systems, okay, and the variables x and y. Okay, so for 16, we got 4x plus 2y is equal to negative 8. 3x minus 2y is equal to 29. And what I can do here, okay, so I can, if I add together, 2y, negative 2y go out. 4x plus 3x is going to make 7x. Negative 8 plus 29 becomes 21. And for division by 7, okay, so we're going to have that x is equal to 3. I can go back and plug in for 3 for x in either equation and solve for y. I'll just go over the first one once again. Okay, so if I plug in 3 for x. Okay, so we have 4 times 3, okay, which is going to be 12, plus 2y is equal to negative 8. So 12 plus 2y is equal to negative 8. And if I take 12 away from both sides, I'm going to have that 2y is going to be negative 20. And so with division by 2, we have that y is equal to negative 10. Okay, so x is at 3, y is at negative 10. So 4 times 3 is 12, 2 times negative 10 is negative 20, 12 minus 20 is negative 8, and also 3 times 3 is 9, negative 2 times negative 10 is a positive 20, 9 plus 20 comes out to 29. Okay, so we got x equal to 3, y equal to negative 10, and again, as an ordered pair, we have 3, negative 10. And for what we have in terms of the mixed bag, okay, with a quadratic and a linear expression, then we have for this particular system, not this one. There we go. Okay. All right. So yeah, y is equal to x squared minus 8x plus 2. Y is equal to negative 2x plus 18. And this is one where we can apply substitution. Okay, so we got y equals x squared minus 8x plus 2. Y is equal to negative 2x plus 18. And this one's kind of tricky, but it's still workable. Okay, so for what we have in this layout, okay, so you have y isolated in both situations. But over here, I can go ahead and solve for x. If I substitute for y and solve for x, so for what we're going to have here, okay, so we got x squared minus 8x plus 2 is equal to negative 2x plus 18. And for what we have, if we combine like terms together, so I can add 2x and deduct 18 from both sides. So we're going to have in the rewrite, so we have x squared minus 6x minus 16, okay, is equal to 0. Okay, and so we have with this quadratic equation in standard form, okay, so if I look at factoring, so from x squared we'll have x and x. Factors of negative 16 whose sum or difference will be on the negative side at 6, so we'll have plus 2 and minus 8. And for x plus 2 equal to 0, okay, so we have that x is equal to negative 2. And for x minus 8 is equal to 0, okay, so we have that x is equal to 8. Right. So we have our x values. Now in terms of solving for y, okay, so we've got these two equations, and if you've got different degrees, always go with the simplest equation. Okay, so you're going to plug, and kind of use this as a recommended note of recommendation. And what I mean by the simplest is be like the lowest degree equation. And we have between the entities, so we have y is equal to negative 2x plus 18. Okay, so at x is equal to negative 2, and we have for the corresponding y value, okay, so we have that y is going to be equal to negative 2 times negative 2 plus 18. And we have that y is equal to 4 plus 18. And we had that y is equal to 22. And for what we have at x is equal to 8. So we have for y is equal to negative 2x, we have y is equal to negative 2 times 8. Plus 18. Negative 2 times 8 is negative 16. And negative 16 plus 8, okay, that is going to come out to positive 2. Okay, so we have for the solution, we'll end up with two distinct points. Okay, so we have for the xy combination, okay, so we have x at negative 2. And when x is negative 2, y is at 22. And also whenever x is equal to 8, we have that y is equal to 2. So those would be the combinations x and y that will fit into both equations.